Good, thank you very much. It's my pleasure to be here, even though it's somewhat early in the morning here. And I'm not advancing. So let me try now. There we go. So my task is to talk about neutral lipids, and we've been asked to talk about them in the framework of the lipid maps nomenclature. So these, I want to talk about glycerol lipids primarily, but also cholesterol esters. And the reason for this is based more on mass spectrometry than on the lipid class nomenclature. And even though Michael says this is my favorite class of lipids, I must disagree. I spent most of my career with metabolites of arachidonic acid, but anyhow, we have some experience with these neutral lipids. Now, there's a couple reasons why I've classified these two very different classes of lipids. One being a sterol, and these other being the esters of glycerol. One is that they're very highly abundant neutral lipids, both of these classes. And that can be shown here. This is sort of just a compilation of data which is in the literature, which shows this wide range of concentrations of lipids which can be found in plasma. And the ones which are very high in abundance are these neutral lipids. Cholesterol esters and triglycerides are very, very abundant. So they represent some of the most abundant lipids. The nice thing about that is because there's plenty of sample to be analyzed, so we're not pushing sensitivity of the mass spectrometer. But the problem with these molecules is that these are not ions. So unlike phospholipids or sphingolipids, these things are not charged. So you heard from Maria that one has to ionize these molecules in order to measure the top row are the common neutral lipids found in mammalian systems, and the monoacyl and diacyl glycerols with the sugars of this can be galactose. Those are in plants. You must ionize those. So typically we do that by adding some sort of cationic system, for example, ammonium acetate or sodium, or lithium, as you'll see shortly. And you must do this. Now, it turns out this type of ionization is not as efficient. So we talk about that with the term, the cross-section of ionization. That's not as high for these neutral lipids as it is for something like phospholipids, because ionization of phospholipids, ionized molecules, just involves charge separation as the mechanism rather than cationization. So typically the neutral lipids form positive ions as adduct ions. So that's one of the unique features of these classes of lipids. Now, I have a similar sort of organization as you've heard from everyone else about how one does lipidomics. And the very first part is you got to have a reason for doing this. For example, you're interested in the biochemistry. But the first step starts with lipid extraction, and I'll talk about that in actually my next lecture. And then you can have some sort of mass spectrometric analysis of your extract. And you heard a little bit about the targeted methods. We think those are very useful methods. And then the unbiased methods, the shotgun, and then the chromatographic-based methods. And I'll sort of go through these in that order there. And then after that, you have to really deal with the identification from the data you collect. And that's really one of the, as you've already heard from almost every speaker, that is a critically important step and one where you can make lots of mistakes. So let's talk about the shotgun lipidomics, and you've heard about that from Gerhard, and so it was nice having him first. I won't have to go into a lot of details about shotgun lipidomics, but he showed you a similar sort of spectrum as we see here from Jianling Han, in which they add lithium to make positive ions out of neutral lipids. And if you look at just single MS analysis of that extract, you see positive ions from cholesterol, from phosphatidylcholine, as well as from the neutral lipid, in this case, the internal standard that was added. But the other ions are pretty low in abundance because of the ionization cross-section of neutral lipids is pretty low. And so to find the neutral lipids, you have to do specific, some sort of specific experiment, which you can pull the triglycerides out of the phospholipids. And to do that, you make use of this ion chemistry. And this is the structure of a cationized neutral lipid. And when you collisionally activate them, they lose ammonia and a fatty acid by this mechanism from either SN1 or 3 or SN2, same sort of mechanism of the loss of the fatty acid as a neutral loss plus ammonia in this case. But lithium adducts do this same ion chemistry, and you can see that here. Here's a lithium adduct, same sort of ion chemistry, only in this case it's loss of the carboxylic acid, and you have the lithiated product ion here, either from SN1 or SN2. So you need to look at this chemistry to help you pull out the neutral lipids. So here we see neutral loss of the fatty acids from here, and you can see that you can uniquely find the neutral lipids, which contain stearic acid, your internal standard, 18.2, 18.1, or even 20 with 4. And you can easily pull those out, and now you can see them as unique product ions, which allow you to really do the shotgun analysis and this was described to you by Gerhardt quite well. So the advantages of this is also just to stress what the advantages of these can be. Easily implemented, this kind of shotgun analysis is any lab which has a triple quadrupole or a quadruple time of flight instrument. So any lab which has that, they can easily do this. A large number of lipid species can be detected. I would add the caveat, they probably have to be the major species. The newer instruments with high resolution capability, such as the time of flight or the Orbitrap, really help in this identification process, and even ion mobility, as you've heard from the Bruker representative, that really adds another mention of identification for the shotgun, and those really do help the identification process. I would say that its disadvantages, the minor species are really difficult to detect by this. In biological samples, sodium and potassium adducts can make analysis difficult because it's more complicated unless you control the ion chemistry, for example, through your extraction process. Because you have no chromatography, separation of isobaric species can be really, really difficult, and isomeric species. So here I pointed out the problem, problem with BMP versus phosphatidylglycerol. That was a problem that Sven also talked about, which he solves by using ion mobility. So the shotgun analysis, really fast, easy to implement. It has some major difficulties, and I think Michael really pointed out very clearly what some of the difficulties can be with shotgun analysis. So what about the chromatographic-based lipidomic studies? So indeed, with neutral lipids, you can use reverse phase. You saw great examples of that, normal phase and Hillick. And I'm going to add thin layer chromatography to this discussion here, because that's something else that you can think about rather than offline analysis. Now, I'm going to show you normal phase analysis. And as Michael correctly pointed out, this can be really difficult if you run normal phase in a way in which you have water present. But if you do not have water present, so this happens to be a tertiary butyl ether and hexane, you can get very nice separation of these classes of lipids, but you can't do electrospray ionization. So what we do is we add, at the end of the HPLC column, we add the charging ammonium acetate to a solvent which can become miscible with your mobile phase. We mix them in a tea right before we electrospray them, and this allows us to do electrospray ionization very nicely with this class of lipids. So here's a separation of a normal phase separation. We ran it pretty quickly, and the cholesterol esters came out very early. If we would have to lower the percent of the ether to get better separation. But here you can see triglycerides come out quite nicely as a class of lipids. There's some separation of species. And then here we have the diglycerides and then some ion suppression because cholesterol is coming off at this point here, and monoglycerides even later. You get a few free lipid type molecules. You get a prenolipid, ubiquitin-9 which is present in the sample, and you get, of course, contaminants like phthalates coming off. Let me point out this. This MEDGS is a code we use for ether triglycerides. So one of the acyl groups is not an ester, but an ether. And you can get very nice separation of these by this technique. So here you can see coming off at this very early time point are all the cholesterol esters. And if we take a look at these, you can see that these are the molecular ion species for the cholesterol esters, and one can, of course, quantitate from that. Now, LCMS and LCMS-MS, and we'll talk about that shortly, with normal phase, we think is really very important. And I would certainly agree with Michael. It really improves identification, much more difficult with reverse phase. He really nicely pointed out, so I took out anything which might prove that point. He proved it quite nicely. I would maintain improved sensitivity quite a bit because you can separate these species, these neutral lipids, from the phospholipids, for example, which are present in much higher concentration in some samples. Now, the disadvantage of this is there's an overhead of time, and that reduces efficiency. I have always thought that one could be penny wise and pound foolish with time. If you really get very good separation of species and therefore improve identification, you just change time that you spend with separation. With time, you have to separate with dealing with the problems of identification. So anyhow, I think that disadvantage is not as much as what other people think. Okay, what about targeted lipidomics? Now, I sort of explain how we use that for some of these neutral lipid classes, and we use them for the cholesterol esters. This is a little bit of targeting using precursor ion scanning or MRM, and I'll explain both of these. So here we have precursor ion scanning, which we do at the very beginning of the elution of the LC column. And here we look at the precursors of this ion 369, the cholesterol ion here at 369. And you can see here's the one way the cholesterol ester 668. When you collisionally activate that, you get a big ion 369. So one can monitor 369, and when you do, you see you can pick up the precursor ion 668 when Q1 is scanning at 668. So here's an example when we're looking at a sample of the peritoneal macrophage, and we're looking at precursors of 369. You can see all of these cholesterol esters, and we've even picked up some oxidized internal standards, which you can get, and even some oxidized cholesterol esters. This is a short chain cholesterol ester 9L. Now, the MRM type approach, one scans Q1 through a cyclic process. So there's a duty cycle, as you've heard from Rebecca. When you do this, there's a duty cycle and you worry about this, but you only monitor 369, And very nicely, you can get all these different molecular species if you program in these ions and sequentially go through them. You can get the abundance of these. And this is a very nice way since you probably know by pre-analysis what the species are for the cholesterol esters, and you put them in this rather straightforward MRM cycle. So you can get very nice data for these molecular species here. So what about identification of the neutral lipids? This could really be the most challenging part of this part, and I think that spending time on chromatography at the beginning can reduce that time quite significantly. So you always have to put that into your equation of how long it can take to do this. There has been some very egregious errors in the literature, which I've had to observe in my role of the editor of a journal, where people think they have identified some compounds as neutral lipids, and they're just totally wrong. And they use database searching without much thought or actually reviewing of the data themselves. And this is really an important part of identification. Now, I'm going to sort of talk the remaining part of my time here about some quantitative issues. And Michael very nicely illustrated some of the issues about quantitation. First of all, to do quantitative analysis, that's relating the ratio of your target ion versus divided by the internal standard signal. And the issue is that for the number of carbon atoms and a number of double bonds, you can get different responses. And so you have to do a calibration curve. So this is mean you have to add a known standard to calibrate your internal standard. And here's the slope of the line for a fully saturated molecule, the red line for two double bonds. Here's with a longer chain, there's a different species, and even double bonds, there's even a third, a fourth calibration line. So the problem is your accuracy of quantitation is related to the availability of your, what I would call your reference standard material, which you have in your lab. And you may not have very many of these. And for neutral lipids, we don't have very many standards available unless you go through the effort of synthesizing them in your own lab. Or that you've gone through the trouble of separating and purifying something like vegetable oils or plant oils, where you have a large number of these. Most labs have to buy these, and when you buy them, there's not many out there commercially available. So you have limited availability of standards to do these accurate quantitations. So I want to talk a little bit about quantitation more theoretically here. There is a relationship between the signal you measure is the mass to charge and the concentration of the lipid. So that signal you get is a function of lipid concentration. It's also a function of the ionization cross-section, which is what this problem is for neutral lipids and when you have to make adduct ions with them. And ionization cross-section of phospholipids is much higher, so that's good. Another factor is ion stability. How stable is that ion that you are producing? And some ions are not very stable. So for neutral lipids, they have pretty similar ion stability, but this does differ by the ion stability does differ by the double bonds and chain length. There's also instrumental factors. So your relationship between your concentration of your lipid and your measured mass to charge intensity could be different with different machines. And that's a known feature. And there's some other factors here which I think aren't as major as what these are. So how do you get rid of all these variabilities? Well, one is to use this internal standard method. And that's why everyone that you've heard so far talks about using an internal standard. So you can divide the response of your sample that you want to measure divided by the internal standard. And so what you're left with is you've just brought it down to just ion stability, ionization cross-section, and the lipid. Now you can reduce this even more by having them co-elute at the same time, as Michael told you. And that really helps why we like normal phase. They look very similar. And so we can reduce some of those issues. But you would need a reference standard for each of these molecular species if you want an absolute quantitation, and to get these standards, and that's this problem right here. And so if you use a stable isotope internal standard, and this is what we've always used for measuring icosanoids, you get a perfect relationship and eliminate the problem of ionization and cross-section and ion stability. And so the concentration of lipid is very nicely related to the ratio of the measured mass to charge ratio and internal standard. And these slopes actually come very close to unity, if not perfect unity. It depends on the purity of the internal standard. But the reference methods are really important to at least reduce you down to this sort of relationship. And you have to live with the fact that you can't correct for ion stability and ionization cross-section because you have different internal standards. So that leads us to this other issue about quantitation versus absolute quantitation, relative quantitation versus absolute. Now, targeted lipidomics allows you to do absolute quantitation if you have an internal standard for each and every analyte, and that's unlikely for a large number of lipids, and in particular, the neutral lipids. When you have an internal standard, which is maybe one or two, but maybe just one, you're going to have a problem with then your response factors are going to be different. Now, the reference standards which you use to make these standard curves, you worry about their purity. But I always like to point out the internal standard which you use for quantitation, you don't worry about purity. In fact, very often you ignore the fact that it's not fully deuterated, and all you rely on the fact that it's the ratio of the internal standard, and that purity divides out when you do the calculation. But the amount you add is critical when you use that internal standard. These sort of issues become sort of cancel out if you use the relative quantitation approach, because there you are ratioing your signal to the internal standard, and the same factors which controlled the ion stability and the response factors, they sort of cancel out. So the fact that you don't have the same response, well, you're going to measure that response across each sample you're comparing, so that the fold change, and typically there we say what's the fold difference rather than what the absolute quantitation, that becomes a constant feature. So this becomes a quite nice way to actually look at how lipids change relative to each other. It doesn't allow you to cross into other people's research, but it does tell you very precisely what is happening with your experiment. Okay, let me turn now to diglycerides. They're sort of an interesting feature, the diglycerides. So they are, they come from this biochemical pathway, of course, de novo synthesis. They also come from degradation of more complex lipids, and they can also come from degradation of triglyceride. I didn't show the arrow backwards. They could come from hydrolysis of triglycerides. So diglycerides are really important lipid intermediates, and measuring them can become a very useful thing to do if you are studying the biochemistry of your lipids. Now, I've chosen to show this slide. Now, this is imaging mass spectrometry, and imaging mass spectrometry you're going to hear about later, but typically they use matrix-assisted laser desorption ionization, and this is a human liver tissue slice, and we have done multi of that, and I've given you the image of the ion at 881. In the liver, you can see there's some interesting images there. But I've shown you this because there have been several papers, and one is too many, but there have been several papers which have used imaging mass spectrometry and interpreted what the images are. And in particular, I will want to point out these ions at down here at between 550 and 600. They were interpreted as diglyceride ions. And I don't think they are diglyceride ions. I think these ions have come from the decomposition of some of these ions up here because of the very facile ion chemistry and the instability of the ion, which happens when you do multi-mass spectrometry. So for those to be diglyceride ions, they would have to lose water. And you typically don't form this sort of ion. You may have a sodium, an ammonium adduct if you added ammonium acetate. The sodiated ions, which are more likely present in a tissue, are very stable, so they don't easily do that chemistry. I don't think that's happening, but I think they came from, for example, the decomposition of the protonated PE species by this ion chemistry here, losing the polar head group as a neutral loss. So, loss of the polar head group here to form what I call diglyceride-like ions. And those are these ions at 577. So I always like to point out that you got to be careful about how you interpret some of this data. And in particular, when you see these ions, this diglyceride ion, this could come from a diglyceride if it was an ammoniated species, but it won't come from a sodiated species. Now, to get around this problem of uniquely identifying diglycerides, because they can be confused with other species, we've gone to derivatization of diglycerides with this isocyanate to form the diphenolfluorine, diphenolfluorourethane derivative. And that just forms another ester, which just nicely forms an attachment ion. And it decomposes by losing, of course, ammonia and then the diphenolurethane derivative as an acid. Or it could also lose either one or the two acyl groups, and you can also form acylium ions out of this. And when you do normal phase separation of these, you get an added benefit of, you get very nice separation of 1,3 diglycerides from 1,2 diglycerides. Sometimes you see some things unexpected. Now I'm going to talk about these ions here. And unfortunately and these monoglycerides, you can also separate 1 monoglycerides from 2 glycerides. And here are the I'm not sure why. Okay, here are the 1,2 diglyceride region. You can see that is now characterized by the loss of 190, which is that diphenolfluorourethane, and you can interpret those spectra. And then if you look at this spectrum, which is the 1,3 region, they're very different. There's the 1,2, sorry. I'm sorry, I didn't show you. I took that one out. The 1,3 is very different. Now, the unknown compound I showed you there are very strange. You see these are very unique things. And one of the most abundant species is a 40 carbon with 7 double bonds, and 38 with 6, and 42 with 9. Very strange. But the question we had is, does this really have 7 double bonds in it? That's sort of unusual. So we looked at the 839 region. That's the region right here, 839. And we see that we have 2 peaks, probably for the for some isomers. And when you look at the mass spectrum of the 139, the most abundant, you see the acylium ions down here. You see the loss of ammonia in 1 fatty acid, the loss of ammonia in another fatty acid, the loss of ammonia in a 3rd fatty acid. And you see its acylium ion is also present. And you see the loss of a 24 with 7 double bonds, and it's plus some neutral ammonia. And you see that acylium ion there. So all of those are present in there. It's a mixture of 2 isomeric species. So what could they be? Well, here's our suggestion. One could be 18-1, 22-6, adds up to 40 with 7. And this one could be 16-0, 24 with 7. What is 24 with 7? Well, we think that is due to the biosynthesis of DHA. So the biosynthesis of DHA comes down from 18-3, 20 with 5, 22 with 5. And for a while, there was an argument about whether that's a delta 4 desaturase to go to 22-6. We know that's not true. What happens is it's elongated and then desaturated to 24 with 6. And then if you do the first round of beta oxidation, you get 24 with 7. Complete beta oxidation, you go down to 22-6. So the 24 with 7 turns out to be a beta oxidation intermediate. So anyhow, I just want to use that as an example to show you sometimes this derivatization is a useful process to find something unusual. So diglycerides are very important precursors as metabolites in cell. They can be misidentified, especially in imaging experiments. There's some publications out there which say diglycerides are present in high concentrations in tissues. I don't think that's true. It's very simple to make derivatives of these, and there's some useful features about them and how you can really identify them. So the conclusion of this, and thankfully I was able to make up some time because of the wonderful presentations that Rebecca and Sven and Maria, as well as Michael, had before me, that these mass spec-based methods of lipidomics can be very powerful for neutral lipids in particular. You can use both shotgun and chromatographic based mass spectrometric approaches to help you analyze the lipid extracts and identify them. I think that the developments in the hardware, as you heard from both SciEx and from Bruker, are continuing to improve our ability to identify these compounds, and in particular software development. So quantitation, I would say relative quantitation is easily implemented. You just need to add an internal standard, and then you ratio the intensity to that internal standard. And that's going to be a valid ratio in terms of some quantitative terms across the same samples where you added the same internal standard and analyzed them in the same relatively short period of time from each other. And so you can look at differences, really very subtle differences between lipid expression or presence in extracts across the biochemical study in neutral lipids. Now, to study absolute quantitation, you have to have reference material. The key is the reference material, not the internal standard, since impurities of the internal standard cancel out, but the reference standards don't cancel out. The number you think you have made for the concentration of the reference standard is going to be how accurate your method is. For neutral lipids, it's a big problem because of the number of internal standards, the number of reference standards which you have available to do this. So that's sort of some of the caveats about the quantitation. I would add to this that my recommendations are that you separate, if you're going to look at neutral lipids like the cholesterol esters, diglycerides, and triglycerides, the one you seriously consider normal phase chromatography as a way to do this. And in particular, the newer methods with helic chromatography, we have used those also. They work very, very well. But you probably will have to add a makeup solvent system so that you can do electrospray ionization. With that, I think that is the end of what I want to talk about. And I'll be glad to answer any questions.